Welcome to Educator.com. In this lesson, we're going to take a look at basic types of numbers. We'll see that there's many different ways that you can take numbers and start to classify them. I'll go over all these types of numbers more in detail as we see how a number gets into each of the groups. We'll also see how you can represent these numbers on a number line. This will be handy for, say, comparing numbers and really figuring out what it means to take the absolute value of a number. We'll also see some symbols on how you can compare numbers, leading to our inequalities. So when it comes to numbers, you can really break them down into various different groups and classify them according to their properties. Some of the most common types of groups that we can use to classify numbers are the natural numbers, whole numbers, integers, rationals, irrationals, and imaginary numbers. We'll go over each of these groups in more detail. In our first group, we'll take a look at the natural numbers. These are the numbers that do not contain any fractions or any decimals. In fact, they're sometimes called the counting numbers because they are some of the first numbers you learn when counting. They contain the numbers 1, 2, 3, 4, 5, and they really just go up from there. So again, notice how we don't have any fractions, no decimals, and actually no negative numbers here. In the next group, we start expanding on that last list just a little bit, and we also include the number 0. Now, since we have all of the same numbers that we had before, these are our natural numbers, and we have that number of 0, you could say that all natural numbers are a type of whole number. Watch for this to happen a few different times as we go through these groups of numbers. Some numbers end up in more than one group. The important part with this one is that they contain the natural numbers and 0 in order to be a whole number. Alright, continuing on. We can also expand on those numbers by looking at the integers. The integers not only include, say, the natural numbers, but the negatives of all of our natural numbers and 0. So again, this makes all of our natural numbers and our whole numbers a type of integer. And you can see from the list, we got some nice numbers on here like -3, -2, -1, there's 0, 1, 2, 3, 4, all the way up on that side. Now, the rational numbers are probably one of our most important groups. These include all numbers that can be written as a fraction. Now, there's many different types of numbers that you can write as a fraction. In fact, all the numbers that we just covered previously can easily be turned into a fraction by putting them over 1. The harder ones to determine whether you can write them as a fraction or not are the ones that involve decimals. But here's how you can tell if they are rational or not. If that decimal terminates, that means it stops, then you know you can write it as a fraction, therefore it is rational. If your decimal goes on and on forever and it has a repeated block of numbers, then you may also write those as fractions, so they are rationals. To help you figure out some of these, let's look at a few examples and see why they are all types of rational numbers. The first one I'm looking at here is 3/17. Notice how this one is already a fraction. So it's a pretty obvious choice that you can write it as a fraction, so it is rational. This number 4 could have been one of our numbers on our natural number list. And it is also one that we can write as a fraction fairly quickly by simply putting it over 1. So again, since we can write it as a fraction, we know it is a type of rational number. Let's look at the more difficult one. These are the ones that involve decimals. In 0.161616 repeating, this one goes on and on forever and ever. But it has that 16 that just keeps repeating over and over again. That's what I mean by repeated block of numbers. Since it has that repeated block, it can be written as a fraction. In fact, this one's written as 16/99. So I know that it is a type of rational number. Alright, the next one. 0.245, and then it stops. Because it stops, this is a type of terminating decimal. So it can be written as a fraction as well. In fact, you can count up the number of places in it and just put it over that number. So tens, hundreds, thousands. There we go, written as a fraction. So again, look for these types of numbers when determining your rational numbers. Now, if we know what numbers can be written as a fraction, then we must also talk about the numbers that cannot be written as a fraction. These types of numbers are irrational numbers. Now, we saw many different types of numbers that could be written as a fraction, so it seemed like there might not be a whole lot that you can't write as a fraction. But it turns out there's many common numbers that simply cannot be written as a fraction. Some more of the common ones are roots that cannot be reduced any farther. Also, if you have a decimal that goes on and on forever, and it doesn't have a repeated block of numbers in it, then that is a type of irrational number. There's also many famous constants which happen to be irrational numbers, and they show up in many different areas. So again, look at my examples below to see why they are irrational numbers. Here, when looking at the square root of 57, I know that this does not reduce. In fact, if you decide to punch this one into a calculator, you'll see that it has a decimal that just keeps going on and on forever, and it doesn't have a repeated block of numbers. So that's how I know that that one is irrational. This next one's a little bit more clear to see, because I can actually look at its decimal and see it has no repeated blocks, and yep, it goes on and on forever. So it is irrational. Then we have a very curious number at the very end. This is one of those famous constants. Pi is equal to 3.141592, and then it keeps going on and on forever, and it does not have a repeated block of numbers in it, so I know that it is irrational. Now, all the types of numbers we've covered thus far are actually types of real numbers, but there's another group that is completely distinct from those real numbers. Those are the imaginary numbers, and you can usually recognize those ones because they'll contain an imaginary part with I in it. Now, the reasons why these will be so important is some equations might only have imaginary numbers as solutions. We'll learn more about these imaginary numbers in some future lessons. Now, as I've said before, they are completely separate from our real numbers. So you won't have an imaginary number that also ends up on our list for real numbers. Completely different things. Here are some examples of some imaginary numbers. When looking at 2i, I can see that it has the I right next to it. So definitely imaginary. 1 over 2 plus 5 over 7i. Again, I can see that I sitting there. This is one of our complex numbers, but it is an imaginary number for sure. And now on the end here, I have the square root of -1. Well, I don't see any I in that one. Why does it get to be an imaginary number? Well, we'll learn that imaginary numbers come from taking the square root of negative quantities. In fact, the square root of -1 is equal to I, so it actually is an imaginary number. To really understand why some numbers get to be on multiple groups, you really have to take a step back and look at the big picture for this classification. I've drawn out a nice diagram so you can see what numbers end up in which groups. The most important distinction that you could make between numbers is probably whether they are real or imaginary, since those groups are completely separate. You'll notice in the real category, we can go further and start breaking that down into many other different types of numbers. Again, we do that according to their properties. The next most important distinction we make is whether we can write it as a fraction, we call those rationals, or whether we cannot write those as fractions, we call those irrationals. All right, and notice how I'm connecting things with arrows here. I'm doing that to show how these categories break down. So rational numbers are types of real numbers, and irrational numbers are types of real numbers. Okay, continuing on with those numbers that can be written as fractions, those are the rationals. Now we move on to integers. You'll notice at that stage we kind of drop away all of our fractions. We don't have decimals anymore. Now we have numbers like -2, -1, 0, 1, and we go on from there. As we continue classifying them, we get to our whole numbers. In these ones, now we don't have any more negatives. So we start at 0, we have 1, 2, 3, and we go up from there. All right, and on to our probably most simplest list. Those are the natural numbers. So they start at 1, 2, 3, and they go up from there. Remember, these ones are known as our counting numbers. Now, one way that you can use this diagram to help you classify numbers is to know that if a number ends up in one of these categories, it's also in all of the categories above it. And we can see this happen for some of our numbers. Like, let's take the number 2. I can see that it's definitely on my natural number list. But it's also a type of whole number. In addition, it is a type of integer. And I could take 2 and write it as a fraction, so it is a type of rational number, which is of course a type of real number. So 2 gets to be in all of those categories above it. Let's take one that's not in quite as many groups. For example, let's just take the square root of 3. It's an irrational number. But it's also in the category above it, so it is a square root of 3. And it's a type of real number. Okay, not bad. Now that we know a little bit more about the different types of numbers, let me show you how you can visualize a great way to compare them using what is known as a number line. On a number line, we draw out a straight line and mark out some key values such as like -3, -2, all the way up from there. We put the numbers that are smaller on the left and the larger numbers on the right. So in this way I can make good comparisons between numbers. So I can see that 0 is on the left side of 3, so I could say that 0 is less than 3. Now it's handy to be able to visualize numbers in this way when looking at their absolute value. The absolute value of a number is its distance from 0 on a number line. So as a quick example, maybe I'm looking at the absolute value of 2. Well, since 2 is exactly 2 away on a number line, then I know that the absolute value of 2 is 2. Let's try another one. How about the absolute value of -3? That one I can see is exactly 3 away on a number line. So its absolute value is a +3. Now you might develop some shortcuts and say, wait a minute, the absolute value just takes the number and always makes it positive, and that's okay. That's the way it should work. That's because our distances are always positive. Now as long as we can go ahead and compare numbers, we might as well pick up some new notation for doing this. You can compare numbers using inequalities and use the following symbols. You can use greater than, less than, greater than or equal to, and less than or equal to. The way these symbols work is you want to put the smaller number with the smaller end of the inequality sign, and the larger end of the inequality sign with the larger number. So I could say something like -3 is less than 5. And that'd be a good comparison between the two. Alright, so we've seen a lot about classifying numbers and comparing them. Let's go ahead and practice these ideas by classifying the following numbers. So let's see if we can list out all of the groups that the following numbers belong to. I'm going to start with 2/3. So first I'll think, is 2/3 a real number or an imaginary number? Well, I don't see any eyes on it, so I will call this a real number. Okay, now I need to decide, can I write it as a fraction or not? Well, this one's already a fraction, so I know that I can write it as a fraction for sure. I will call this a rational number. Alright, moving on from there. In my integers, those contain the numbers like -3, -2, -1, 0, and up from there. Notice how in the integers we don't have fractions, we don't have decimals. So this one does not get to be in the integer group, or anything below that for that matter. Okay, so I could say that 2/3 is a real number, and I could say that 2/3 is a rational number. Let's try another one of these. 2.666 repeating. Well, I don't see any imaginary parts, so I will say that this is definitely a real number. Can I write it as a fraction? Well, I do see it has a repeated block of numbers that goes on and on forever, so it is a type of rational number. Okay, what else can I say? Is it an integer? Nope, it has the decimal part on it. It is not an integer. So I'll leave that one as it is. Alright, moving on. The square root of 3. This is a type of real number. It doesn't have any imaginary part on it. Can I write this one as a fraction or not? Well, this one I can't. In fact, if you look at the decimal, you'll see it goes on and on forever, and it doesn't have that repeated block of numbers. So irrational. Now, since we don't have any more distinct groups below irrational, we'll go ahead and stop classifying that one. All right, on to some other numbers. -5. That is a type of real number. Okay, looks good. Can we write it as a fraction? You bet. We'll simply put it over 1. So it is rational. Okay, is it an integer? Well, it doesn't have any fractions, doesn't have any decimals, so I will say that it is an integer. All right, is it a type of whole number? Well, there's where I need to stop. Whole numbers do not contain negative numbers. All right, so -5 is real, it's rational, and it's an integer. On to the number 0. This one gets to be in a lot of different groups. 0 is a type of real number. You can write it as a fraction, so we will say that it is rational. It is a type of integer, since it sits between our negative numbers and our positive numbers. And it is definitely a whole number. Now that's where this one really stops getting classified, because the natural numbers start at 1 and then go up from there. All right, one more. Let's classify 9. This one is a type of real number. We can write it as a fraction, so I know that it is rational. It is definitely on our list of integers. It is also a type of whole number. And we can go just a little bit further with this one. This is a type of natural number. So 9 gets to be in a lot of different groups. It is a type of real number, a rational number, it is an integer, it's a whole number, and it is a type of natural number. Now let's try this in a slightly different way. Here I have a giant group of numbers. We want to list out whether the number is in some of our various different groups, like imaginary, real, irrational. That way we can think of visualizing, classifying them in just a slightly different way. So let's start off with the first one. I want to figure out all the groups that -7 belongs to. Well, I know that it is a type of real number, so let's go ahead and put it into that group. Now, can I write this as a fraction or not? Well, yeah, I can write it as a fraction, so let's put it in our rational category. Is it a type of integer? Yes, it is on my integer list. Is it a type of whole number? No, because our whole numbers do not contain negatives, so we'll stop classifying that number. Let's try another one. Negative the square root of 3. That is another type of real number. However, that one I can't write as a fraction, so I better put it in the irrational category. And then that one's done. Moving on. -0.7. It is a type of real number. This one can be written as a fraction. It's -7/10. So let's go ahead and put it in our rational category. Okay, can we go any farther from there? Well, unfortunately not, because it contains those decimals. And integers don't contain decimals, so we can stop classifying that one. Moving on to 0. 0 is a type of real number. It is a type of rational. It is a type of integer. And it is a type of whole number, so it gets to be in a lot of different groups. Remember, it is not a natural number, since that starts at 1 and goes up. On to 2/3. That one is definitely a real number. And since it's already a fraction, I know it is a rational number. It is not an integer, since it is a fraction, 2/3. The square root of 11. It is a real number, doesn't contain any imaginary parts. This one cannot be written as a fraction. And so I'll put it in the irrational category and then stop classifying that one. Alright, on to our famous number here, pi. Pi is a type of real number. Even though it's a little unusual, does go on and on forever, it is type of real number. It is irrational since I cannot write it as a fraction. Okay, then we'll stop classifying that one since there's no other distinct groups below irrational. On to the number 8. This one's going to be in a lot of different groups. It is a type of real number. I can write it as a fraction by putting it over 1. It is on our integer list. It's on our whole number list. And it is a type of natural number. So lots of different things. Alright, on to 15 halves. I will say that that is a type of real number. I can write it as a fraction, so let's put it in our rational category. Unfortunately, it is not an integer, so I will not put it into that one. The number 12. 12 is a type of real number. We can write it as a fraction by putting it over 1, so let's put it in rationals. It is a type of integer. It is a type of whole number. And since the natural numbers start at 1 and then go 2, 3, 4, and all the way up from there, I know that it is a natural number. Okay, just one more to do. The number 3i. Well, I had to throw in an imaginary number on my list, so it will immediately drop that into the imaginary bin. And that's all the more classifying we will do with that one, since again, imaginary numbers and real numbers are completely distinct from one another. And you'll notice that most of these categories are all types of real numbers. Okay, so now that we've classified numbers, let's get better about comparing them on a number line or just being able to plot them out. So the way we plot out a number on a number line is we find it, say using one of our markers below, and put a big dot where it is. So if I want to graph something out like 3 on a number line, I find 3 and I place a big old dot right at 3. Now, once I plot it out, I can do some good comparisons. So we can see that since 3 is to the left of 4, that 3 is less than 4. Or in a similar way, since 3 is on the right side of -1, then I know 3 is greater than -1. So let's plot out a few more. -2 on a number line, we'd find -2 and go ahead and put a big old dot there. When it gets into fractions and decimals, it does get a little bit more difficult, but you can still put these on the number line as well. So this one is 5/3, and I don't see any 5/3 in my little markers here on the bottom. What I can do is I can break down each little section into thirds and then mark out the 5th one. So 1/3, then more thirds, and more thirds. And we're looking for 5/3. So 1, 2, 3, 4, 5. We'd put that big dot right here. Now we can better compare where 5/3 is into other numbers. So 5/3 is less than 2, but it is greater than 1. Alright, -3.75. That would be the same as -3 and 75 1/100ths. Now that can also be written as -3 and 3/4. So that tells me I need to break down my number line into quarters. Half, quarter, half, quarters, half, quarters, half, quarter, and half quarters. Okay, so I'm looking to mark out 3 whole sections and then 3/4. And we're going in the negative direction. So 3, 1, 2, 3, and we will put a big old dot there. Okay, so we can see that -3.75 is greater than -4, and it is also less than a -3. Let's use our number lines so that we can actually line up various different numbers and see which ones are smaller than the other ones. This will be just a rough sketch of the number line, so I'm not going to be too accurate with my tick marks. But I'll really just use it so I know how they compare to one another. Alright, so let's go ahead and start with our first number here and put -7 on our number line. Since it is a negative number, I'm going to aim for somewhere on the left side here. Negative 7. Negative 3 is a little bit more than that, so I'll put it on the positive side over here. And we'll put a spot there for 3. Negative 0.7. Well, that's not very big. I know it's definitely larger than negative 7 and less than 3. So let's go ahead and put it maybe right here. Negative 0.7. Zero is a good number. So we can put it greater than negative 0.73. And 2/3 is larger than 0, so we'll put it on the right side. All right, on to something a little bit trickier, the square root of 15. Well, I know that that is less than 4, since the square root of 16, something a little bit larger, would be on the right side. It is greater than 3, since the square root of 9 would be 3. So I'm going to put this one larger than 3, square root of 15. All right, 8's a good one. Definitely larger than the square root of 15. Mark that one off. Negative 7/2. Well, that one is about negative 7.5. I mean negative 3.5. Let's put that one down here. Negative 7/2. Negative 5. And one more number, pi. 3.1415, a little bit larger than 3, so we'll put it a little bit larger than 3. All right, now that we've used our number line to really get some comparisons among all of these, we'll simply list them from smallest all the way up to largest. So negative 7, negative 5, negative 7/2, negative 0.7, 0, 2/3, 3, pi, square root of 15, and 8. Not bad. All right, for this last example, we'll go ahead and use our inequality symbols like less than or greater than to go ahead and compare these two numbers. If you want, you can use a number line to plot them out before using these symbols. All right, so let's try the first one, comparing 6 and 2. When I plot these out, 2 is on the left side of 6. So I know that 2 is less than 6. It's my smaller number. So I will draw my inequality symbol so that I show that 2 is less than 6. I could also say that 6 is greater than 2. Let's try another one. Negative 7 and 5. It's tempting to say that negative 7 is bigger, but our negatives are on the left side and our positives are on the right side, so I can see that negative 7 is really less than 5. So let's write that out. Negative 7 is less than 5. Negative 5 and negative 3. Well, negative 5 is further down than negative 3. So I know that it will be less than a negative 3. All right, and one more. 2.3 and 5.7. 2.3, 5.7 would be much larger. So I know that 5.7 is greater than 2.3, or in the order that they're in, 2.3 is less than 5.7. So these symbols are really handy in showing the comparison, especially where they are on a number line. Now, one thing I didn't use here is the or equals to symbol. I could have put that in for all of these spots, so 6 is greater than or equal to 2, or I could have said -7 is less than or equal to 5. That's because it also takes into the possibility that the numbers could have been equal. The reason why I didn't is I can see that all of the numbers are not equal. And it is a little bit more flexible when using this other one. Watch the or equals to symbol to show up when we're doing a lot of our inequalities. Alright, and so these ones are good. Thank you for watching Educator.com.